Hello dear friends, a great welcome to this series on engineering mechanics. Myself Jaraj MP. This is the class 7 of the series and it covers the following topics. 1. Introduction to cross product of vectors, and second, moment of a force about a point in the vectorial format. So let us start our class. So before introducing the moment of a force in the vectorial format, let me first introduce you to one basic operation in the vector algebra, that is the cross product of vectors. Now, as per the definition, the cross product of two vectors, vector A and B, yields the vector C, and it is represented as vector C equal to vector A cross vector B. Now let us define the magnitude of vector C as well as the direction of vector C. The magnitude of vector C is defined as the magnitude of vectors A and B and the sine of the angle between their tails, where the angle between their tails theta lies between 0 and 180 degrees. That is, the magnitude of C equal to the product of the magnitudes of the vectors A and B, that is A into B, into the sine of the angle between their tails. Now, obviously, the vector C has to be defined also with respect to its direction, because just now we have written only the magnitude. Now, vector C has a direction that is perpendicular to the plane containing vector A and vector B, such that vector C is specified by the right hand rule. So look here. Here we have shown a vector A and also a vector B. We are interested in the cross product of vector A and vector B. That means we are interested in vector A cross vector B. And look here, theta is the angle between the tails of vectors A and B. So in order to find out the direction of vector C, where vector C is vector A cross vector B, we need to follow some criteria. Number one, the vector C is perpendicular to the plane containing vector A and vector B. So as you can see, that the plane containing vector A and vector B is indicated by a gray dark color, right? And now here, number one, vector C is normal to the plane containing A and B. So now the question is whether vector C is directed upward or downward. And this will be determined by the right hand rule. So what we need to do is that we are talking about A cross B. So it does mean that we have to move in the anti-clockwise direction from A to B as marked here. So what we do is we curl the fingers of our right hand in the anti-clockwise direction to find that the thumb is pointed upward, which indicates that in this case vector C is directed upward and it is perpendicular to the plane containing A and B, and it passes through the tail point of vectors A and B. So this is how we fix the direction of vector C. Now look here, here is another sketch wherein I am carrying out the same operation A and B. In this case, we can say that C A cross B, we have to curl the fingers in the anti-clockwise direction, right? So number one, vector C, it is perpendicular to the plane containing A and B. I'm going to curl the fingers of our right hand in the anti-clockwise direction, indicating that the thumb is pointed upwards. That is, C, vector C is directed upward. Now here is a case where we are performing for the same vectors, not A cross B, but B cross A. Look here, for B cross A, we have to move from B to A, right? So we have to curl the fingers in the clockwise direction. So when you curl the fingers of your right hand in the clockwise direction, you find that the thumb is pointed downward. So that is minus C is B cross A. So here we find that A cross B and B cross A, they have the same magnitudes, but their directions are exactly opposite. One is directed vertically upward and the other one vertically downward. So let us now get into some of the simple properties of the cross product. For any two vectors, vector A and B, we have vector A cross vector B will be equal to minus of vector B cross vector A. And this property is already demonstrated in these two sketches. Now, if A is a simple scalar quantity, we can do the straightforward multiplication with a cross product. That is, A into across B can be taken as A into vector A cross vector B, then vector A cross A into vector B, and that's equal to A cross B into A. Now we have defined completely the meaning of the cross product A cross B. Now let us extend this definition of the cross product of any two vectors A and B to the cross product definition among the unit vectors. Obviously we know that the unit vectors are nothing but we talk about I, J, K, where I, J and K are the unit vectors along the Cartesian positive x-axis, positive y-axis and positive z-axis. So let us for example, let us find out what is I cross J. Remember here I is a unit vector, J is also a unit vector. So what will be the magnitude of I cross J? It is magnitude of I, that is 1, into magnitude of J, that is 1, into the sine of the angle between I and J. That means the angle between x and y directions, that is 90 degrees. So 1. So we find that the magnitude of I cross J is 1. So I cross J will also yield us a unit vector. Now what will be the direction of I cross J? It is very simple. We apply the same thing, same right hand rule. Look here. So I is the unit vector along the x-axis. J and K are the unit vectors along the z-axis, y-axis and z-axis. Now look here. We are interested in I cross J. So to apply the right hand rule, what we do is we curl the fingers. We are carrying out I cross J. So we have to curl the fingers of the right hand in the anti-clockwise direction. And in this case, we find that thumb is directed upwards, which means that as far as I cross J is concerned, its direction is along the positive z-axis. Okay, positive z-axis, and also we know that the magnitude of I cross J is unity. So which means that I cross J is equal to its magnitude. What's the magnitude? It's equal to 1 into the unit vector along its direction, that is K. So which means that I cross J is nothing but K. Okay. So now there is a simple rule. So we cannot memorize all this, vector cross product between different combinations of the unit vectors. So the best way is that what you do is you write I, J, K, okay, in the anti-clockwise direction along the circumference of a circle. Any cross product that is carried out in the anti-clockwise direction or counterclockwise direction will provide a positive result. Any cross product that is carried out in the clockwise direction will yield a negative result. For example, just now we discussed about I cross J is equal to K. So I cross J, from I to J we are moving in the anti-clockwise direction, means we will have a positive result. So the result will be I cross J, it will provide us K. On the other hand, let us take for example the J cross I. J cross I, we are moving in the clockwise direction. It does mean we will have a negative result, that is equal to minus K. So J cross I is equal to minus K. Now it is very easy for us to conclude that the cross product between any two same vectors will provide us a zero vector, because let us for example I cross I. What is I cross I? Its magnitude will be 1 into 1 into sine of 0, because the angle between the two similar vectors will be 0 only. So indicating that the cross product operation between the same vectors will provide us a zero vector. Remember that this is not 0, this is actually 0 vector, right? So we have now learned how to carry out the cross product operation between any two unit vectors. Now in many cases we know that the vectors are normally provided in the Cartesian format, that is in the format axi plus ayj plus azk. Let us assume that the vectors a and b are provided us in the Cartesian format, so that vector a cross b can be written as axi plus ayj plus azk, and bxi plus byj and bzk is defining the vector b. So in these expressions, please remember that ax, ay and az are the magnitudes of the components of vector A along the positive xy and z axis, and bx, by, bz are the magnitudes of the components of vector B along the positive Cartesian axis x, y and z. So let us just carry out the cross product between the various terms and expand it. We will arrive at the expression as shown here. Now we know the result of the cross product between the various unit vectors. For example, we know that I cross j should be k, and we know that j cross j should be 0. So substituting all the results of the cross product operation between the successive unit vectors, we can simplify this expression as vector a cross vector b as aybz minus azby into I minus of axbz minus of azbxj plus axby minus aybxk. And this can be written conveniently in a determinant format. That is, vector a cross vector b can be easily evaluated in a determinant format. So what we have to do is, we just write down a determinant, and the first row of the determinant will be occupied by the unit vectors ijk. The second row will be occupied by the components of the first vector, that is vector a, that is ax, ay and az. And the last row will be occupied by the components of vector b, that is bx, by, bz. In this way, we will be able to carry out the cross product operation between any two vectors that are expressed in the Cartesian vector format. So we have now a far better understanding of the cross product operation and how to evaluate it in a determinant form also. And also we have seen how to carry out the cross product operation between the unit vectors. Now with this concept in our mind, let us go ahead with the definition of the moment of a force about a point in the vectorial format. Now the moment of a force vector F about a point can be defined as vector MO is equal to vector R cross vector F. So let me explain this equation by making use of this simple sketch. Look into this sketch. So let me just drag this a little bit. Yes. Okay, look here. So this is my point O, right? And this is my vector F. So what we have done is, we would like to calculate the moment of this vector F about the point O. So as you can see here, the position vector R, the vector R is drawn from the point O about which the moment has to be calculated to any point A on the vector F. That is very important. Okay, so I am repeating, vector R is always drawn from the point O to any point A on the line of action of F. So we have vector F, vector R, and obviously we know that, okay, MO, that is the moment vector, it will have a magnitude and it will have a direction as well. So let us now prove, yes, vector MO, that is the cross product, let us prove that the cross product operation R cross F will define the magnitude and direction of the moment about the point O in all sense, right? So let us first focus on the magnitude of vector MO, right? The magnitude of vector MO, which is nothing but the moment of the force F about the point O. So let us see, the magnitude that is obtained by this expression matches with the formula that we had already derived during our scalar discussion, right? Scalar format discussion. So now let us see what will be the magnitude of R cross F here. As per the definition of the cross product, obviously we know that if vector MO is written as vector R cross F, the magnitude of vector MO can be written as MO is equal to magnitude of vector R, that is R into, which I have written over here as R into F into, that is the magnitude of my force, into the sine of the angle between their tails. Look here. So this is my force F, and this vector R, I just continued it so that I confirm that yes, theta is the angle between the tails of vector R and vector F. Okay, so we find that the magnitude of the moment calculated about the point O due to the force F has got a magnitude of how much? Rf into sine theta, right? Now Rf into sine theta can be written as F into R sine theta. Now looking into this figure, it is very easy for us to say that if R is this distance, okay, and theta is this angle, what is R into sine theta? It is nothing but, it's the perpendicular distance d, which is nothing but the moment arm that we have discussed in the scalar format session. Okay, so this means that F into d. So this is what is written here, which agrees with our magnitude. So please remember our discussions while we were evaluating the magnitude of the moment about a point in the scalar format. So we made one conclusion, that is r cross f has a magnitude that is equal to f into d, where d is the perpendicular distance from the point O onto the line of action of the on the line of direction, okay, of the force F. Now let us talk about whether r cross F provide us the right direction or not. Now looking into this figure, we know that, look here. So this is r cross F. So number one, as we have already discussed in the earlier session, MO is a vector, right? MO is a vector. We should pass through the point O, right? We should pass through the point O, and it should be perpendicular to the plane containing R, D, and F. Or in this case, when we carry out R cross F, we obtain vector MO. This is what is written here. Vector MO is R cross F. Now let us investigate what will be the direction of vector MO. As per the cross product operation, we know that the direction of MO should be perpendicular to the plane containing vector R and vector F. Look here. This is my vector R. This is my vector F. So it lies in the same plane. Okay. It does mean that my vector MO should be perpendicular to this plane. So it matches with our earlier, perception. That means the moment vector must be perpendicular to the plane containing F and D. Now, obviously we know that. Now the question is whether this moment vector which passes through the point O, whether it should be directed upward or downward. Now we are talking about R cross F, from R to F. So we have to curl the fingers in the anti-clockwise direction as shown here. So we find that the thumb is pointed upward in this case. So we come to the same conclusion of the direction of the moment vector. The same conclusion we made in the earlier session when we were discussing the direction of the moment vector in the scalar format. We arrive at the same conclusion here as well. This means that the moment vector computed using R cross F provide us the same magnitude and same direction as we derived in our earlier session. So to conclude, we mean that the moment of a force, to calculate the moment of a force F about any point O, first of all, you need to draw a position vector R from the point O to any point A on the line of action of the force F. So we have vector R and vector F. Now the moment vector about the point O is easily computed as the cross product between vector R and vector F. And we have just now proved that R cross F can represent the moment vector, okay, properly, both from the angles of magnitude as well as direction. Now let us find out. So we know vector MO is vector R cross vector F. Now in major applications of the computation of the moment about a point in space, we express R and F in the Cartesian vector format. Accordingly, let us assume that vector R takes the form Rxi plus Ryj plus Rz, where Rx, Ry and Rz are the magnitudes of the components of vector R in the x, y and z directions. Let us assume that vector F has taken the value Fxi plus Fyj plus Fzk, right? So accordingly, vector MO can be written as vector R cross F. So which can be easily obtained as, we have to just simply put it in a determinant form, with the first row being ijk, the second row being the magnitudes of the components of vector R, that is Rx, Ry and Rz, that is the position vector drawn from point O to any point on the line of action of vector F, and the third row obviously being the components of vector F, that is Fx, Fy and Fz. And here I would like to introduce you one of the very important property of this computation of the moment, as I already discussed just now. See, look here, this is my force F. and I would like to calculate the moment of this force F about the point O. Now how to draw the position vector? You have to draw the position vector from the point O. O is fixed from the point O to any point on the line of action of F. So means you can draw this position vector either to this point as represented by vector R1 or to other point as represented by R2 or to another third point which is on the line of action of vector of to obtain vector R3, and whatever may be the point you choose on the line of action of vector F, you will find that all of these position vectors will provide us the same moment vector about the point O. That means vector MO can be written as vector R1 cross vector F, or can be written as vector R2 cross vector F, or vector R3 cross vector F. Means that the value of the moment vector computed at the point O, it do not depend upon the point chosen on the line of action of vector F for the definition of the position vector R. This is an important conclusion. Now, in many cases, as we have discussed, our rigid body in space may be subjected to a set of different forces. For example, look here. Here is the rigid body, and this is subjected to a set of forces F1, F2, and F3. So, how do we calculate the moment of these forces F1, F2, and F3 about the point O? Or let us calculate the total turning effect produced by F1, F2, and F3 about the point O. So, it's very simple. What we have to do? Let us first focus on the calculation of the moment due to force F1 about the point O. So what we have to do, first obtain the position vector from the point O about which we would like to calculate the moment, draw a position vector to any point on the line of action of F1. So R1 is defined. Similarly, also define R2 and R3, which are nothing but the position vectors drawn from the point O to any point on the line of action of vectors F2 and F3. Now obviously we know that the moment of F1 about the point O is R1 cross F1, and that of F2 is R2 cross F2, and the moment produced by F3 about the point O is R3 cross F3. Extending this reasoning, we know that if a rigid body is subjected to a set of forces, the resultant moment computed at any point O can be written as sigma of R cross F, where R indicates the position vector associated with any force F. So what we do is that we compute the moment produced by the individual forces in a vectorial format and add them in a vectorial format only. Okay. So we will have the conclusion for this class. So we find that the computation of the moment of a force about a point is obtained through the cross product operation. Okay, so we will demonstrate the application of the computation of the moment about a point in the vectorial format in the next class through some selected 2 or 3 examples. So let us conclude this class. Thanks a lot for listening.